In this lecture, we'll discuss about D'Alembert's principle. Okay. Discussing about D'Alembert's principle, we'll also talk a little about Newton's second law of motion, which is more or less similar to the D'Alembert's principle, right? But it is to understand that both of them are different and has different purposes. Okay. So according to Newton's second law of motion, if there is a resultant force acting on the particle, okay, then the particle will have an acceleration in the direction of the force applied, and the magnitude is proportional to the magnitude of the force applied, right? So let's say that there is a particle at this point subjected to three forces, F1, F2 and F3. Okay, so there is a resultant force on that, which is F. Okay, so when this particular force is applied on the particle will have an acceleration along the direction of the force applied. Okay, and this force will be proportional to the magnitude of the acceleration. Okay, so F is proportional to A, which means that F is equal to m into A, where m is the mass of the particle and is a positive scalar quantity. This is what second law told us. Also, when there is number of particle forces acting on a body, okay, let's say that the resultant of all these forces is sigma. In that case, we can mathematically write sigma F is equal to mass into acceleration, where A is the resultant acceleration along the direction of resultant force, right? Now you can note that when the sigma F, the resultant force, becomes 0, okay, you can also say that from the equation mass cannot be 0, however A can be 0, so resultant acceleration will also be 0. Okay, so this particular statement, when the net force is 0, the resultant acceleration is also 0. This is very closely related to the Newton's first law of motion, which states that the body continues to be in a state of rest or state of motion unless an external force acts on it, right? So this is nothing but our first law, right? So you can see that from second law only you can directly obtain Newton's first law. So it is also to be noted that both force and acceleration are vector quantity and mass is a scalar quantity. Okay, so this vector quantities can be resolved into individual components along the rectangular coordinate system, okay, x, y, z, right, by taking the projection. So you can also write that instead of writing sigma F is equal to ma, you can also write the same equation in terms of its components. So sigma Fx equal to mass into Ax, where Fx and Ax are the force and acceleration components along the x direction. Similarly, you can write it for sigma Fy and sigma Fz. Okay, so that's about Newton's second law of motion. So it always talks about inertial force, right, where F is equal to m into A. This F is nothing but inertial force equal to inertia, right? Now let's see what is D'Alembert's principle. So according to D'Alembert, a problem in kinetics or a body in motion can be solved by using the principle of static only, that is using the equilibrium conditions only, if you include an inertial force which is equal in magnitude and opposite in direction to the acceleration along with the all other forces acting on the body which causes the motion. Okay, so this particular state, when you include an additional inertial force in the direction opposite to the acceleration of the body, is called as dynamic equilibrium. Okay, so now let's see that. So let's say that there is a body of mass m, okay, which is applied with two forces F1 and F2, which is having a resultant R. Okay, so when the resultant force R acts on the body of mass m, the body will tend to move along the direction of resultant, let's say with an expression A. Okay, so this particular body is in a kinetic state or a dynamic state. Okay, it is in a motion. So if you want to analyze this particular body, what you have to do is you have to include an equal and opposite force vector of magnitude, mass into acceleration. Okay, but in the opposite direction to the resultant force. So this particular thing, ma reverse and r together will be in a equilibrium, which means that r minus ma reverse will be equal to 0. So this particular force vector ma reverse is called as inertia force vector. We use the symbol reverse to indicate that the direction of force vector is opposite to that of the acceleration. Okay, so this particular state r minus ma reverse is called as the dynamic equilibrium. Fine. Second, r is nothing but the resultant force. So this is the expression for D'Alembert's principle, r minus ma is equal to 0, where r is the resultant force and a is the ma is the initial force vector. Okay, so again this can be resolved into components and solved. Sigma fx minus max equal to 0 and sigma fy minus may equal to 0. Fine. Let's see a practical example. One of the most commonly experienced thing is a motion in lift. Okay, so when a person is moving in a lift, okay, or the lift as such is moving upward, you can see that we will experience more weight. Okay, so let's see how it is. So let's say that the total mass of the lift is m. Okay, and let's say that it's moving upward with an acceleration of a. Okay, let's say that r is the tension in the pull or tension or pull in the cable which is lifting the lift, and of course due to mass the weight always acts downward and its magnitude is equal to w is equal to m into g, right? So you can see that acceleration, so this particular thing is in a dynamic state because this entire system is moving upward with a velocity acceleration of a. So in order to bring it to dynamic equilibrium, what you have to do is you have to put a force vector exactly opposite to the direction of acceleration. So you put a force vector opposite to the direction of acceleration, and acceleration is upward, so we put force vector downward and its magnitude will be mass into acceleration. Okay, so now all these three forces are in a dynamic equilibrium, which means that all the force together summed together in y direction should be 0. This indicates that sigma fy equal to 0, which implies r is equal to ma plus mg, which means that the reaction or the pull increases by an amount m into a. So reaction or the pull on the lift will be m into g plus a. Fine. Similarly, you can analyze when the lift is moving downward also. So when the lift is moving downward, we have a downward acceleration. Okay, and the weight is obviously acting downward, so its magnitude is again m into g. Okay, so this is in a dynamic state or kinetic state. So acceleration acting downward, which means that we'll have to include a inertial force vector in the upward direction. So in upward direction, inertial force vector and its magnitude is mass into acceleration. So this particular force, the reaction force or the pull force and the weight should be in equilibrium. So sum of all the forces in y direction will have r plus ma is equal to mg, or r is equal to mg minus ma, which means that the reaction reduces by an amount of m into a, or the weight reduces by an amount of m into a. Fine. So this is one application of D'Alembert's principle. Let's see in the coming lectures. Thank you.